Kia ora, and welcome to another online tutorial. Today we're going to be talking about centre of mass, specifically what it is, the formula we use for calculating centre of mass with multiple objects in play, centre of mass during collision, and go through an example NCEA question. Alright, let's get to it. So, what is centre of mass before we even start? Let's define it. So, centre of mass is the point at which all the masses on an object appear to be concentrated as far as the object's motion is concerned. To put it simply, in terms of the balance, it's the point of an object where an object must be supported to remain balanced, and I've given an example down here, a very professionally drawn one, of just a hammer with its centre of mass just below the neck, and if you put your finger there you could balance the hammer, that being its centre of mass. But again, simple example with a single object. Today we're going to be talking about if there's multiple objects. Cool, so when we do have multiple objects, we use this formula here, and it's our formula for the centre of mass, with xcm being the distance from a reference point, because we're always calculating it from one of the masses, or centre of masses usually, typically. Okay. M being the mass of an object, and we have given numbers and used n as a filler here, and x the distance from that reference point to the other mass, or the other centre of mass. Okay, we always deal centre to centre. So we have it up here, nothing too crazy. It's the sum of all the masses and their distance times together, okay, divided by their masses, and we get that as a distance, the sum of which gives us our cm, our centre of mass, from our particular reference point. Okay, some things to note and to think about. Okay, so our centre of mass doesn't have to be contained within an object. So if we have a more complex shape, sometimes the centre of mass might actually fall outside of the object. Okay, if you think about if you're doing a workout or something like that and you do a bridge, or if you're very flexible, bend yourself over in an arch, your centre of mass is actually going to be below your belly, somewhere in that middle of that arch. Okay, and it would fall outside your body, and it can fall outside an object the same too. So we have an example here of when you apply a force to an object that doesn't have has an offset centre of mass. So we can see we've got three objects here that have a very low centre of mass, which I've marked with these black dots. Okay, and I'm applying a force perpendicular to that at a given place, and we can see that there's a force and a distance. You're going to generate a torque, and these objects, when torqued, will actually rotate around or about that centre of mass. Okay, it's pretty simple. Thinking back to level 2. Now, where it gets a little bit more confusing for a lot of people, and remember we're focusing on this particular example with external forces, we've got two objects that are about to collide. Okay, object 1, object 2. As they're moving, okay, we can see that their relative centre of mass is moving too. Okay, and I've denoted that with a marked line, a dotted line. Okay, they have an impact, bam. Impact, we know that their velocities are going to change, okay, but our momentum P is going to be conserved. Okay, they're now traveling in this direction, but you can see that the centre of mass has not changed. Okay, and we want to note that the centre of mass remains at rest or at constant velocity unless an external force is acting on the system. So if we have a closed system here with no external forces acting, okay, the centre of mass will continue. If the centre of mass is stationary, it will stay stationary. If the centre of mass is moving at a velocity, it will maintain that velocity unless you applied an external force. Okay, cool. So we are going to have a crack at an exam question. So the example we're going to use today is NCEA Mechanical Systems exam 2017 question 1 A to C. Okay, so I'll read you the question. It says, two astronauts, Sylvia and Sam, are on a mission to another planet. During they're doing a spacewalk outside the ship. Oh, sorry, I'll just get this sorted here for a moment so I can actually see. So Daisy, to the side. Wrong one, wrong one. Should set this up before I end up so Daisy. Cool, so start fresh on that one. So the example we're looking at today is NCEA Mechanical Systems Examination 2017 question 1A to C. I'll start off by reading that question to you. Two astronauts, Sylvia and Sam, are on a mission from another planet. During their journey they are doing a spacewalk outside the spaceship. At one time they are freely moving, as shown in the diagram which I'll crudely draw. They collide and they stick together. Okay, so I want to draw a really really crap picture really of them. This is going to be my Sam, okay, who has a mass of 105 kilograms, okay, and is moving with a velocity of 1.2 meters per second. All right. Oh, I should have thought this out earlier. That's Sam. Sylvia, who I'm going to denote because there's also an S with a V, okay, is moving this way, and they have a mass of 95 kilograms, and they're moving at a velocity of 1.4 meters a second. So a little bit heavier, moving a bit slower, a little bit lighter, moving a bit faster. Okay. So for the first question A, they want us to calculate the distance between Sam and the center of mass in the system when he and Sylvia are 4.8 meters apart. Okay, so for A, I want to knock the tripod here, I'm going to draw a diagram. Okay, so we've got our two center of masses, a given distance which is 4.8 meters apart. Remember, when you're doing your questions, the more drawing, honestly, the clearer it gets. 4.8 meters, we've got Sam, we've got Sylvia. Okay, and Sam has a mass of 105 kilograms. Okay, and Sylvia has a mass of 95 kilograms. So, using our equation from before, which we have here, okay, we're going to use this equation to find out the center of mass between two objects. So, relatively simple here. We're just going to say our distance to our center of mass from our reference point Sam is going to be our distance Sam times our mass Sam, okay, plus our distance Sylvia times our mass of Sylvia over their two masses, M Sam plus, or the sum of their masses, M Sylvia. Okay, so all I'm going to do now is plug and chug, put the numbers in, okay, and I get XCM equals our mass from Sam to Sam is 0 times his distance, sorry, and his mass is 105 kilograms, plus our mass, or our distance of Sylvia, sorry, which is 4.8 meters, times her mass, which is 95. Okay, we know 0 times something is going to be 0, so we're just going to cross that out here, make it nice and easy for us. And we're going to get these two numbers over here. We're going to get 105 plus 95. Okay, so we actually do some calculations on this, and we will get these two numbers, and that makes it 200. Quick calculation, strong mental maths, should equal 2.28 meters. Okay. Remembering that we give our unit because we're doing distance, and then we use our standard index unit where possible. Okay. Relatively chill. Going on to B. So in B, they ask, describe what happens when the center of mass of the system as the astronaut move closer together and when they collide. So they're asking what's happening at the center of mass, or to the center of mass of the system when they move closer together and when they collide. And we discussed this earlier, so let me find this. Okay, if these two are moving through space, okay, and they've got no force acting upon them, it's a closed system, no external forces, we know that this center of mass is going to stay constant, or at a constant velocity. Okay, so what do we say? For this one, it's pretty simple. We'll just say it stays the same. So it says describe what happens to the center of mass. Say the center of mass would remain same, because no external forces are acting upon them. You can put that in. The justification can be no external forces, or it's a closed system. Both are fine. Okay. Now for C, we're going to calculate the astronauts' combined speed after they collide. So we're going to have a little bit of thinking here. An object that's moving is going to have momentum, and we're going to use this momentum to calculate, and knowing that it's conserved, the momentum of them both moving post. It's going to be the same as them both together, and then we can rearrange the equation to calculate velocity. So for C, I'm going to start off saying that P equals mv. Okay, and actually I'm just going to pull this up here for a moment because I had my working on a separate tab and then it just disappeared. Cool. Alright. We know P equals mv, and therefore we can say our Psam equals 105 times his velocity, mass times velocity, right, which is 1.2, which is going to give us a momentum of 126 kilograms per meter squared. Oh, per meter, sorry. Per meter a second. Whew. Now, P Sylvia, I'm really struggling to spell Sylvia here actually. Okay, equals her mass times her velocity, which is up here 95 times 1.4, and that gives us our answer of 133 kilograms meter a second. Okay, so that's the first step. We've calculated their relative momentums, and we know that that is going to be conserved post collision. Okay, so what we can do now is do a little vector diagram. So cool, so we have our vector diagram here. We're going to put our momentums on. Momentum being a vector, it has both a quantity and a direction, so it involves that velocity. So I've got 126 going this way, 133 going this way, and I want to know this one here, our x. Okay, I'm going to call these A, B, and C, and we can do a little bit of Pythagoras and say that A squared equals B squared plus C squared. Alright, and then if we want to get rid of the square and find out our A or our X, we're going to square root that. Okay, and then it just knocks it off. We square root both sides, gives that equation. If we plug the numbers in, we get it equals the square root of our two numbers here, 126 squared plus 133 squared, and that comes out at roughly 183, and then our units kilogram meters per second. Okay, now we've got our equation here. This is our P, our momentum. P equals mv. Rearrange that to make velocity, the subject of the equation. So v equals P over m. We've got that there. We know the two masses add together to make 200. 95 plus 105. So we can put in velocity equals 183 over 200, and we get 0.92 meters per second, and that's how fast they'll be moving after the collision. Okay, so we've calculated where their center of mass would be relevant to SAM. We've talked about why the center of mass would remain moving in the same direction. It's a closed system, no external forces acting on it, and we've done a little bit of math, used the understanding of vectors and Pythagoras to calculate the velocity post-collision. So again, hope that helps. I'd really recommend getting out there, getting into it, doing a few examples, and using this as a guide if you get stuck. Good luck.